When a black hole appears in a sci-fi movie, it usually acts like an inescapable cosmic vacuum cleaner, sucking up planets, stars, and ships without warning. But that's pure fiction. In reality, a black hole is just mass. It happens to be incredibly compressed mass, but it still obeys standard gravitational rules, governed by strict mathematical laws. Its pull depends entirely on how heavy it is and how close you get. If you were to replace our sun with a black hole of the exact same mass, the solar system wouldn't get swallowed up. Earth's orbit would remain a perfectly steady circle because the total gravitational pull in the center hasn't increased at all. The actual danger to Earth isn't our sun collapsing. The threat lies in a rogue stellar mass black hole, an object packing the weight of dozens of suns, drifting into our solar system from deep space. Because a wandering black hole emits no light, we wouldn't see it coming. Our only warning would be the gravitational chaos it triggers as it crosses the invisible spatial boundaries of our planetary neighborhood. The absolute edge of our solar system is the Oort cloud, a massive spherical shell filled with billions of icy bodies and comets loosely held by the sun's gravity. When a stellar mass black hole passes through this distant region, Earth doesn't feel its direct pull. Instead, the intruder's massive gravity creates a violent scattering effect among the ice and rock. This disruption acts like a shotgun blast, launching a relentless barrage of comets toward the inner solar system, placing Earth directly in the crosshairs. If the black hole keeps approaching and reaches 100 astronomical units, just past the orbit of Pluto, it begins to seriously compete with the sun's gravitational dominance. Watch our outer planetary orbits. Uranus and Pluto are physically stolen from the sun, dragged into orbit around the intruder. Losing outer planets forces the entire solar system to rebalance. The barycenter shifts drastically, stretching Earth's circular orbit into an extreme ellipse. The black hole is still billions of miles away, but shifting our gravitational center seals our fate. This elliptical orbit would drag Earth far out into the freezing dark, then throw it dangerously close to the sun, ensuring all life perishes in either a global ice age or extreme heat. But if the black hole continues inward and crosses Saturn's orbit, its gravity begins to outright overpower the sun's hold on the rocky inner planets. This diagram maps out the habitable zone, the narrow, temperate band around the sun where liquid water can exist. As the black hole nears, Earth is physically dragged outside of this safe boundary, stripping away the specific conditions required for liquid oceans. Once the massive object crosses Jupiter's orbit, Earth is finally caught in the black hole's direct tidal pull. We would stop orbiting the sun entirely and begin orbiting the black hole itself. The final threshold is the orbit of Mars. At this close range, the direct gravitational stress placed on our planet reaches its peak destructive potential. Earth gets subjected to extreme tidal forces. The intense difference in gravity pulling on the near side versus the far side stretches and compresses the planet. This relentless friction buckles the crust and forces glowing magma up to the surface. The geological friction generates so much heat that global surface temperatures spike, causing the remaining oceans to boil and evaporate entirely into space. By the time a black hole reaches Mars, it doesn't need to suck Earth into a dark void. Gravity alone melts the planet back down into a sterilized sphere of magma. In the wake of this passage, Earth is left as either a lifeless, glowing ember orbiting a dark patch of sky, or it gets torn completely apart into a ring of planetary debris. Fortunately, the statistical odds of a stellar mass black hole drifting through our solar system are incredibly close to zero. We routinely track asteroid threats because the solar system is packed with them. Black holes, however, are exceptionally rare, and the chances of one making a direct pass through our tiny neighborhood are microscopic. The main reason we are safe is geometry. Interstellar space is overwhelmingly, unimaginably empty. The sheer volume of nothingness provides an enormous physical buffer against wandering celestial objects. This leaves our sun as the master of its domain. For billions of years, its reliable mass has dominated the behavior of everything out to tremendous distances, providing the exact gravitational stability needed for life to take hold and evolve. We don't need a massive planetary defense system to survive the universe's most destructive objects. Our protection is the vast, silent void of space, and the uninterrupted, delicate balance maintained by our own star.